this stuff is not the theoretical, like can we do it? We can do it. The limits are how fast you can do it and how much memory you can actually access and process. So that's the rate limiting thing. They've got, they have all digital radar right now at low frequencies, but it's, there's a lot over it. It's very expensive.
When you're talking about low frequencies, are you talking about the carrier or the
Yeah,
pulse
carrier.
rate?
No, the carrier is always the limit because your carrier tells you how fast you have to sample. If you think about Nyquist criteria, twice the highest frequency of interest. That means it's twice the carrier frequency as a sampling frequency.
Well, software-defined radio is still, well, okay, I see what you're saying.
But we'll
It
get
usually there's a down conversion.
You can,
for-
if you're going to do something to bring it to an intermediate frequency, and there's
Right.
tricks, there's a lot of tricks that we'll get to, all right? But the real problem is this. With any of these things, the sampling rate is excessively high, and they have to quantize it too.
Like, there's no way they're doing 52 gigahertz sampling, right? And they have 26 gigahertz, right?
Yeah, there's always an IF stage.
I know, I can show you this later. I know what they're doing. I mean, they're not doing it at 52 gigahertz, they're doing it at 1 gigahertz.
Okay.
And so twice that is 2 gigahertz. They're not at 26 gigahertz.
Okay.
They're going there, and there's tricks. By the way, we don't have HDMI, do we?
You should.
I have a cable.
No, I mean, we don't have it here to feed, do we? I don't think so. That means I have to go back to old reliable, VGA. I'm not a fan of VGA, but I'll tell you, it beats not having anything. I thought for sure that they would update this audio-visual equipment in here. There's no, but you don't see it. There's no feed. Is there an HDMI feed on that thing?
No.
You're kidding me, really?
No.
It's a very old projector.
Well, you know, thank God we have a projector, so I'll just work with what I got.
It's VGA in and out.
What's that?
It's VGA in and out for some reason.
Just bear with me on this one. I want to do this because if I'm referencing this stuff, I'm going to do the proofs here. You can just look in the book. The book has a few things wrong too. Oh yeah. One thing, everybody wants to bring it down to baseband, right? That's what the goal of any processing is. It's getting it there is the hard part. All right, at least I got that. Give me 1 second. Ah, good. I'll just tell you, this is chapter 8, and we're going to start not right there, but right here, and then we're going to keep moving on. All right. Now I'm going to reference this stuff. If this thing shuts down, I'll just restart it. I didn't bring my power supply, but it's not a problem. So here's what I'm going to do. You've already gone through the Fourier transform stuff. You made sure you know. Just to recount a few things, if we have a pulse function, p tau of t, can you get all the lights for this one, please? Thank you. Just turn them on. P tau of t, I know that the function looks like this. It's basically this function. Somebody asked me about this, I think it was you. It's tau over 2 to minus tau over 2. It has a height of 1. This is in the time domain. The transform of that is tau times the sinc of omega tau over 2. Now I'm using the definition of sinc that he doesn't use, but we will make it work. The definition I'm using for the sinc function, sinc of x, is sine x over x. What his definition of sinc is, and this is, I'll call it his, h, is equal to sine of pi x over pi x. The reason they do that is then the zeros are at 1, 2, 3, and 4, and that's the reason they use that function. It's only because it's easier to discuss. Y'all follow me on this? Now, when we go here, we have to know what that function looks like, and I'm going to do the magnitude of that function, what it looks like. We know that the function doesn't have that, but the magnitude of the function looks like this. It is a symmetric function. The peak of this will be tau. This is that, really when you look at this, is when omega tau over 2 is equal to pi. And that means 2 pi over tau is omega. Now if we do it in f, and he likes working with f, we divide by 2 pi. So we say f01 would be equal to simply 1 over tau. So this point right here is 1 over tau, and this is minus 1 over tau. Right here. And this is the main lobe, it's called. Everybody with me on that? Just so you get a visual, that's magnitude of sync of, in this case, it would just be pi f tau. That's the way it looks. And you have to make sure you see this. The next function we have to deal with is this. And I want to try to put this down here. We know delta t simply transforms to 1. Correct, class?
Correct.
In the frequency domain. You all know that, right? Now, if you use duality, and it's been a while, duality says if I take this guy over here and from the frequency put him into the time domain, so if one exists in the time domain, that's DC voltage. Think of it that way. It's been on forever. In the frequency domain, I come over here and I grab this guy and I multiply it by 2 pi, and then I change the argument to minus omega. But the thing is, when you have a delta function, this is going to be a delta, right? Of minus omega is the same thing as delta is plus omega. You all follow me on that? Because it occurs at omega equals 0. I'm just making sure you understand the trickery. All right, so now we have this pairing too. DC goes to that. Next thing I have to mention, I think, is everybody's got this, right? The next thing I have to mention when I'm doing this, and this gets really kind of important. Sometimes you get casual about it, but it's really important. Next thing you have to mention is what happens when you have, if I wanted to take and create an infinite series. So suppose I want to create a series of waveforms like this. I want one pulse, then I want, and this is going to be the actual period t. I'm centering this pulse right there. The reason is it's for mathematical simplicity. So the pulse function occurs at t, it's centered at t equals 0. Are you with me? And then there's another, it repeats itself, right? And let's just say it goes on forever. So it goes on forever. There's going to be an infinite number. I have an infinite number of pulses, and I'm going to call this P train, and you don't have to use my definition of T. He doesn't use that in the book, but he uses a P to indicate both a pulse and an infinite series of pulses, which I don't like. So if I do this, and I want to represent this function, I want to tell you the easiest way to represent it is to think, and I'm giving you some tips when you're doing like graduate work and stuff. Always think of the simplest way to do things. Don't make things more complicated than they need be. There's more mistakes involved usually. So what I have to do is explain one thing. If I have delta of t minus anything, call it nt, and I convolve it with a function f of t, what do I get? We could do the convolution if you want. What is a delta function? What's the one single thing a delta function always does? It sifts, right? It sifts the function next to it at the point where it turns on or goes to infinity, correct, class? Do y'all remember what the definition of convolution is? In case you don't, it might be worthwhile just to mention it. The convolution of two signals, g of t convolved with h of t, is equal to the integral from minus infinity to infinity of g of tau times h of t minus tau d tau. We're going to be using that a lot for matched filter work and also for the ambiguity function. Now, just take a look at this. If we convolve these two, what am I actually doing? I'm going to say the first function is this one, just because this operation could be inverted. You can put f of t first and then delta of t minus nt second. Do you all agree with this? So I go ahead and I do that, and I'm gonna say it's an integral from minus infinity to infinity of the first function as a function of tau, times the second function, delta, but now t is replaced with t minus tau. So this is t minus tau minus nt dt, d tau. And what a delta function always does is it extracts the value of the signal, of anything that's being multiplied with at the point it turns on when it's inside an integration. Does anybody recall that? You all remember what a delta function doing? So where does this turn on? And it's with respect to tau. It would be a tau equals t minus nt, correct, class? Just to show you convolution. We're going to be seeing that over and over and over and over again. So I have to make sure. And you got this. And did you have me for signals? No. You didn't or did it? No? No? Yes? Yes? Yes. Okay, you didn't either. I'm making sure, because I've taught this class and people really were oblivious of how to do a convolution operation. I have to make sure everybody's got this down. All right, now when I do that, that means what it ends up being is simply f of t minus nt. That was my goal of this whole thing. Y'all with me on that? It just extracts the value of the function it's being multiplied by at the point where the delta function turns on. And I'm not worried about scaling or anything like that, because if this was t over a, we'd have to play with it a little. Or if it would be tau in the over a, but don't worry about that. So that means that this function goes to simply f of t minus nt. That's the next thing I do. Are you with me? Now, the next thing after that is making that claim. Now I do this. Now I say can represent this infinite series of pulses, of with tau, and I didn't put it in here, they're with tau, right? And they have a period of t. And remember, t is the PRI, and it's also 1 over the PRF. It's very important that you keep thinking in terms of PRI and PRF and the relationship to t. And I like t, by the way, because it's easier to write. But people use capital T for many, many things in radar work. That's how come they usually specify PRI or PRF when they mean PRI or PRF. So how would you do this? And I'm calling it P train. Well, if we take the pulse function p tau of t and we convolve it with an infinite series of delta of t minus nt, where n goes from minus infinity to infinity, doesn't that do it for us? Sure does. Because now what happens? Now I have an infinite series of simply p tau of t minus nt, where n goes from minus infinity to infinity. And that, in fact, is an infinite series of pulses, all moved by t, capital T, right? When n is 0, it's the center one, t equals 0. When n is 1, now it's centered at capital T. N equals 2, now it's centered at 2t, and so forth. Got it? So that's an infinite series. By the way, does anybody remember doing this in my class that had me? We did this a couple of times for different things. But this is really a clever thing, so remember, anytime you need an infinite set of replicas, convolve it with a delta. But when we do that, now we want to always peek into the frequency domain. We never want to stay in the time domain. It would be foolish. We want to look in the frequency domain because that's where our work's done. So when we take this,
Dr. Baginski, is that an infinity on the last part or an
yeah,
A?
it goes from minus infinity to plus infinity.
Okay, that's
Oh,
like
by the way, we could just get this out of the way. Unless otherwise stated, assume the sum is from minus infinity to plus infinity. All right? Are you with me? What's wrong?
0. I would think it'd be 0, not minus infinity.
No. This is Fourier series analysis. An infinite series has to start at it's been there forever, in other words, that has no beginning and no end. Thank God. Think something like that. All right? Now, when you have that there, we have to see what it looks like in the frequency domain. So, there's a lot of bright people in here. How would you go ahead and take a look at what this thing looks like in the frequency domain? Anybody? Start there. What happens if I have h of t convolved with x of t? What's the best way to take a look at what it looks like in the frequency domain? Take the transform of x of t would become x of omega. Instead of convolution multiplied by the transform of h of t would become h of omega, right? So we're going to do just that. I have already got the pulse right here goes to this. So I've got the pulse transform. Now I need to see what happens to this. But before I do this, and this is nice. And I'm gonna ask you to just watch this. This is the important part that's not in the book. All right, if I have an infinite series of delta of t minus nt, some of you may remember this. N goes from minus infinity to infinity. Y'all agree that's an infinite series of spikes. It's called, what? I call it a bed of nails. I've heard that before. That is called a cone function. Y'all remember? It looks like a cone, right? And I can express that as a Fourier series. If y'all remember, I can express it as a sum. And they use k, but you can use n, from minus infinity to infinity, of some c of k times e to the j n omega naught t. Here, omega naught is simply 2 pi over capital T. Y'all remember doing this? How many remember how to get c of k from an infinite series? No, come on. I know you do, you're just playing with me right now. And you guys know this. The reason I know it is I taught you guys. Your memories need to be kicked. All right, so to get c of k, and that's a Fourier, this is the Fourier series coefficient here. In the book, it's going to have x of n, I think, or x of k, but this is a symbolic thing. It means the coefficient that's going to be there. The way we get it is take 1 over the period and integrate the function from 0 to t, or really go from minus tau over 2 to tau over 2, over 1 period, so I'm going to go from minus tau over 2 to tau over 2, of the function. Well, the function we integrate is this, right? You'll notice if I'm going from minus tau over, or t over 2 to t over 2, it's just delta of t, right? Times e to the minus j n omega naught t dt. Do y'all remember that? That's how you extract. You always take the function, right, that you want the expansion on, integrate it over a period weighed by e to the minus j n omega naught t. Do y'all remember doing this?
Yeah.
Now what is it? Well, when does the delta function turn on? What is e to the 0? 1, right? It's 1 over t. The goal was that. So this is simply, you can put it out here, 1 over t. Now here's where it's important you pay attention. Now I have the infinite series of delta functions going to this infinite series, right? Where it's just of e to the j n omega naught t. By the way, I don't know what that looks like, but I know exactly what it looks like. It looks like this. It's a bed of nails, theoretically. Because this isn't a transform, this is an equality. You all see this, guys? And here's where we have a little fun, sort of. All right. Now, this is really like 1 times that, isn't it? Right? It's 1 times that. Do you agree? What did I say 1 goes to? 1 goes to this, right? Think of 1 as x of t. What happens when I have, I bet you guys remember this, x of t times e to the j omega naught t, assuming I know the Fourier transform of x of t goes to x of omega. What happens over here? Guys, it's going to be, it's going to be x of what? Omega minus omega naught, right? Guys, remember? Y'all with me on that? So what happens if it's n? N. Agreed? And if it's minus, plus. Got me on that? All right, but actually, let's leave it as plus for now. So that's a minus. Okay. Now, why did I do that? Because this 1 looks like my x of t. Do y'all follow me? Now what I'm going to do, I'm taking a Fourier transform of this. Got me on this, guys? And the Fourier transform of this means that the t just scales, right? It's 1 over t, pardon me. So it's just this term. It's the Fourier transform. 1 scales as 2 pi, right, times delta of omega, correct? When it's multiplied by this, what it does is do this. Now k goes from minus infinity to infinity of 2 pi times delta of omega minus n omega naught. And make sure you make a note that omega naught here is 2 pi over t, or it's 2 pi right there times the PRF. That's the pulse repetition frequency. Please note that. He doesn't state that strongly enough. You'll mess this up if you don't. You all agree with me? All right, now, next thing after that, I've got the Fourier transform of this, right here. I've got the Fourier transform of the pulse function right on top there, so I'm gonna need a little breathing room. Tell you what, I'm gonna put this up here. I'll come back and show you all this stuff in a second, because we'll need that, some of this stuff for the Doppler resolution. So therefore, this is important. When I take a look at the Fourier transform of p tau of t convolved with that infinite series of delta functions, t minus nt, capital T, and make sure you know that that is the PRI from n equals minus infinity to infinity, and I want the Fourier transform of that. You all realize that we can take the Fourier transform of this and multiply it by the Fourier transform of that. Do you all see that, class? Now when I do that, I have tau, right, times the sinc of, and this would be omega tau over 2. That's just one of them. Now it's going to be multiplied by the Fourier transform of that, which is 1 over t. So I'm going to put the t out here. And now it's an infinite series of, and I'll put the 2 pi too, 2 pi out here, of delta of omega minus n omega naught. And omega naught there is 2 pi times the pulse repetition frequency. Got me?
Omega naught.
This is, the omega naught is equal to 2 pi over t, or 2 pi over PRI, or 2 pi times PRF. They're all the same. Are you with me? Just watch. This is important because this gets real confusing. Now, ask yourself this. This thing only is infinite whenever omega is at omega naught, right? Do you all agree with that? That's the only time it exists, correct? Agree? So what we can do is take this term and pull it in here and just replace the argument of omega by n omega naught. Do you all see that? So now I can say I'm going to leave the 2 pi tau over t out in front, and now I can take this infinite series, and now I'm going to have the sinc of n omega naught over 2, and then I'm going to have times delta of omega minus n omega naught here, and I left it in terms of n. N goes from minus infinity to infinity, and that is the Fourier transform of this signal.
What happened to the tau and n omega naught over 2 in the sinc function? I think I lost you there.
Let's see, I'm sorry, the tau should be there.
Okay.
This should be tau, my bad. This should be n omega naught tau over 2. That's my fault.
Okay.
I'm sorry about that. Thank you, Marcus. Agreed, everyone? Well, what does that look like? This is important. So what does it really look like? And I'll show you the pictures. Do you have chapter 8 up, Alex?
No, I don't.
All right. Well, if you look in the book, do you have it up, Will? If you look in chapter 8, there's going to be a figure what I'm about to draw, but this is very important. What you've got is spikes. You've got a bed of nails, but it doesn't have a constant amplitude. The amplitude is going to be tailored by that sinc function, right? So let's take a look at what it really looks like. Matter of fact, let's just take a look at the magnitude of this, and let's call this something. So I don't have to keep on. Y'all have this, right? So I don't have to keep on rewriting the whole thing. I just need about this much on the board. We'll call this the Fourier transform, and we'll call it P-tran, or train, of omega. Just leave it as that. It's the Fourier transform of the infinite pulse train, right? Well, what does it look like? Here's the way you do this. First, and let's do the magnitude of it. If I want the magnitude of P train of omega, at 0, when the delta function is 0, the sinc function is 0 as well, right? That would be n equals 0. The sinc of 0 is 1, correct, class? Y'all remember that? Sinc of 0 is 1. Now, that means it starts with this altitude or amplitude right here. It's 2 pi times tau over t. And that's really just the duty cycle, correct? Now, what does it do? Think of it as an envelope, right? Let's just take the magnitude of that. And the envelope's dropping down rapidly. Now let's do this. This is in the frequency domain. I'm going to leave it in the omega domain because we're all bright enough to know if we want the F domain, we divide by 2 pi. Do you agree with me there, guys? That's simple to do. Now, where's the first zero here? Remember, I'm showing this, and instead of n omega, I'm really replacing n omega by just omega, correct? And I'm trying to get it. What I'm trying to do is take this omega right here and just tailor the envelope. Then I'll put in the spikes. You all see what I'm doing? Where's the first zero here? Well, what is it going to be? The first zero of the sine function is, you're right, but I'm trying to just reinforce this, is when this is equal to pi, correct? So if I have omega tau, well, it's actually for f, it would be 1 over 2. It would be omega tau over 2 is equal to pi, or 2 pi over tau is equal to omega. That's the first zero if we're plotting omega. So it's 2 pi over tau here. Here, it's 2 pi minus 2 pi over tau. Agreed? Now, next, where do the spikes occur? Remember, that's tau. Well, the spikes occur what? At 0, so we know we're going to have a spike there, right? The next spike is where? At omega naught, right? What is omega naught? It's 2 pi over t, correct, class? Now, t is less than tau. Y'all with me on this? It's 2 pi over the pulse repetition interval, isn't it, class? Where does that occur? It's got to be less than this, doesn't it? We don't know how much less. Maybe half, maybe less. Somewhere here, there's a spike. By the way, there could be several spikes here. There may be more, depends. And basically what you have is something that looks like this. Now I'm going to talk about something that's very, very important next. And this one you don't want to mess up. So that's the envelope, but that's really what we're going to see if we were in the spectral domain and we had the ability to capture a large amount of a waveform and do a fast Fourier transform and then scale it accordingly. We'll get into scaling and all that in a bit. You remember where we did, if you haven't, you did this. We took a continuous time Fourier transform and we got the information. That's very useful. A lot of that's intuitively obvious. Then we took a DTFT and we weighted by some things so that we could get a direct relationship between the DTFT's results, or DFT, or the FFT, and the actual Fourier transform. Do y'all remember doing that? And we had to go way over sampling to do this legit, but we did it. Well, here's one thing that's very important. Where's this distance here? That is at what? Omega naught, correct, class? Or it's at really 2 pi over t. This first one is 2 pi over t, or really, what is it? It's 2 pi times the pulse repetition frequency. Do y'all see that? That's all the same, that's that. This is at 0. Now, this has to do with Doppler. I'm going to be very clear about this because it gets very, very important. You see what I'm about to say. So I need this board. And this is not brought out real strongly in the book. Chapter 8 and chapter 14 are what we're doing now, and neither one do they really scream about this. I like to really make sure you see it. All right, now answer me this. This is the spectrum of spikes I would get if I have an infinite signal hitting a stationary target and returning. Do y'all see this? This would be the reflected pulse would have the same statistical information, or same signature, only scaled, right, if the target isn't moving. What happens if the target is moving at you? Tell me in a word. What happens to this line right here? Now remember, we took out the high frequency code. I brought it down to basic. Say again?
Moves out slightly.
It's going to move this way, right?
Well, shouldn't it be symmetric?
Well, this is down to baseband, right? Right? If it's coming at it, everything shifts up. If it's coming, going away from it, every shifts down. The whole cone right here, this cut cone, it shifts this way or this way. Now look, if you take a look at this, if it's coming at you, this thing would start shifting up. You all see what I'm talking about? The spikes will move. That means
Wouldn't they just stretch? This Omega Knot
Well, no,
string
no, no, no,
thing?
no. This is an infinite series. It's infinite. It's not a finite. All right, you're thinking about broadening something else that would be.
Wouldn't it go like this?
Nope.
Based on?
Because he has all of the information from all time, you can.
I have a signature, I have a record forever of what came back, and it's been on forever. Now, here's what actually happens. If you just have spikes, we'll get to finite stuff in a second. And here's what you're talking about. If we were not at baseband, if it was multiplied by F naught, then you're up here and you have something like this with a bandwidth, and you would have your basically fundamental up there is F naught. This would be the spike corresponding to this. This is baseband. Are you with me? Now, if it's coming at you, this would shift this way. The entire thing would shift this way. If it's going away, the entire thing shifts the other way. Follow me? It's the entire spectrum, one way or the other. All right? So what does that tell you about the maximum non-ambiguous Doppler shift? Take a look. Well, how far can I shift? Think Nyquist. Can I shift that far? Then you don't know which line you're actually seeing, right? You're going to see a line here, a line here, and a line here. Now, if it shifts a small amount, and I'm going to come over here. Suppose this was the original spike. What if it shifts, and this is the next spike is right here? Well, if it shifts a small amount, and that doesn't exist, now I can look at that and say, yes, indeed. I can find the Doppler shift right there, and I can extract how fast it's moving. Do you agree with me? And here's what it comes down to. The maximum non-ambiguous Doppler shift is omega naught divided by 2 in radians. So write this down. This is maximum non-ambiguous Doppler shift. And this is in radians. It would be F Doppler max would be equal to omega naught divided by 2, or it would be 2 pi over t divided by 2, or if you take a look at this, this is omega Doppler. This is omega Doppler max. And then F Doppler max, FD max, would be that divided by 2 pi, or it would be 1 over 2t, which is the PRF over 2. Write that down. That's the maximum non-ambiguous Doppler shift.
So how does this relate to the velocity of the target?
How many remember what Doppler shift velocity is? This is in baseband.
Right.
Or it's the shift from the carrier frequency. What is it? The way you always remember this, it's twice the velocity right off the bat, and you divide by wavelength.
Right.
And that's the wavelength of the high frequency carrier. Now, a lot of times what they'll do is put this down as it'll be 2VR. It means the component of velocity in the radial direction. It has to be whatever component is along the direct ray from the radar. It can't be the perpendicular component. You got me? You can't read that. You can actually calculate that if you have a range radar that's actually taking data. Then you can take the derivative with respect to position, and you get, dr dt is the exact velocity. It's a vector. But we're not talking ranging radars. These are simply moving target indicating radars. And it's 2V, and then instead of lambda, they'll put C and they'll put F naught here. All right, the carrier frequency, gigahertz, 10 gigahertz, maybe 60, 70 gigahertz. There are radars. Now, I've been told the Russians have radars around 80 gigahertz for target acquisition. At that frequency, you get a tremendous amount of attenuation, so your range goes way down. Ours, we have about, I don't know what CWIS is. Is it 33 gigahertz? Is it, I don't know if it's KU or KA band. CWIS is it's a Gatling gun on most Aegis class cruisers and carriers. And I forgot,
We had them on LPDs.
what was your frequency of transfer frequency? I think it's KA, I think it's 33, but I don't think it's 18. KU is around 18.
We have stationary ones up to 100 now.
What's that?
We have stationary radars up to 100 gigahertz.
But for target acquisition?
No clue what it's used for.
What's that?
I have no clue what it's used for.
Where did you see that?
It's a research station.
that's for, I mean, that's for very small targets. I mean, like, if you're looking for bats or something, maybe that would be. I mean, that's an extremely, that's, first of all, it's tough to do, just to be honest with you. Second of all, it's got a short range.
Yeah.
You're not gonna look at something a mile away with that, I don't think. Unless you're in free space. If you're in a vacuum in space, you can. All right, so that's the one thing I wanted to tell you. That's the maximum non-ambiguous Doppler range, and that's the reason for it. Got me on that? Now the next thing is, what happens when we have a finite, and I should tell you one other thing. In his book, he does not put it in terms of omega. I left it in terms of omega because when I taught signals and systems, we always did everything in terms of omega. And in the real world, you're gonna see most journal articles use omega. However, when you do measurements, almost all equipment is in F. When you look at spectral analysis, it's in F. Now, if you want to turn this in to the frequency domain of F, hertz, you would take omega naught and you would replace it by 2 pi F naught. 2 pi F naught, all right? That's what the book does. One other thing happens is then you have to get rid of the 2 pi there, all right? And I can show you why there, because that has to do with now the definition of your transform changes, all right? And we'll work that problem another time. You had COM here, right? Remember in communications, if you had Jitendra, he always used Fourier transforms in terms of F because they were symmetric. There was no 1/2 pi scaling. It's the same thing here. This 2 pi would not exist if you were an F. But I'm gonna leave it there for the heck of it. Okay, now the fun begins. Now we're gonna go to a finite pulse train. And if I was mean and cruel, I'd make Alex come up to the board and do this proof for half his grade. But I'm not gonna do that. But I am gonna ask for some contributions from the audience. Y'all understand that, guys? This is in chapter 8, and we will get to it. Now, we're gonna get to some fun stuff. So now I have that, and I know this pulse train, I'm gonna repeat it here. The pulse train of T, that's an infinite pulse train that I'm not gonna show again, goes to, and I have 2 pi tau over cap T. And remember, maybe you wanna make sure that you don't mess up that symbol and think it's the actual dwell time or anything. It's just the PRI, right? I'm almost tempted to put PRF there, but I like T over tau because that's a duty cycle. That, in my mind, is something that's very important. A lot of radars have super small duty cycles because they want a tremendous range resolution. The downside is they lose their average power, so they need to collect an enormous amount of pulses with coherent processing to get real information. We take this, and what is it, times, you can put this in first. It's going to be omega minus n omega naught, and again, omega naught is 2 pi over T, and then it's going to be times the sinc, right, of omega tau, or sorry, an omega naught, n omega naught tau over 2. That's what we had over there, right, guys? All right, now we want to take this infinite series. I'm going to erase this. Got a question for you how to do it. All right, I have an infinite series. Now I don't want an infinite series. I want this. I always leave these amplitudes at A. At the very end, I scale everything. I mean, it's 1. At the very end, I scale everything by A, all right, if it's an amplitude. And then it repeats itself. So from here to here is T, and it's going to repeat itself, but it's only going to go out, and now it's going to have a total time. This would be symmetric, even though I didn't draw it symmetrically. Just go with me on this. From here to here, and this is T dwell. This is the dwell time. And T dwell is really going to be M, a certain number of T, where T would be the PRI. You all follow me? It may be 1,000, it may be 10,000. So one dwell time may have 1,000, may have 10,000, may have 100 actual pulses, if you will. Understand? So how would we mathematically deal with that. I wanna cut everything out, but that many pulses. Here I've got P train right here. What do I need to multiply P train by to get it? Matter of fact, let me put it up on the board, then that way you'll see it all. Well, P train I said was what? It was the pulse P tau of T, right? Convolved with this guy, delta of T minus NT, right? Where N goes from minus infinity to infinity. That was P train, correct class? In the time domain. And without any magic, that's the base stuff, right? All right, what do I need to do with that to cull out everything but TD of those? Anybody?
Change the limits.
What's that? I'm sorry, what?
Change the limits?
Well, effectively, that's what we're doing, but we're gonna not change limits, we're gonna multiply it by something. And yes, sure, a pulse function with width TD. Now what you effectively do, you cut out everything but what's inside that, and TD would be M times T, the pulse repetition interval. Are you with me on this, guys? Make sense? Now the fun begins. All right, I still gotta peek into the frequency domain to see what that looks like, don't I? So I know the transform of this, right? That's that, and I'll put it down here. That's 2 pi, right, over T. Then I have this infinite series. N goes from minus infinity to infinity of delta of omega minus N omega naught. And that omega naught, you gotta be sure, that is equal to 2 pi over T. Then it's times the sinc, a sinc function of N omega naught over 2 times tau. That's the first part. Well, that is the Fourier transform of that. What's the Fourier what happens if you have multiplication in the time domain? What does that correspond to in the frequency domain?
Convolution.
Convolution of the frequency domain. You agree with that? Not only convolution of the frequency domain, but isn't it scaled by 1 over 2 pi? Do you remember that? Who has Fourier transform tables available to them? Do you? Can you look that up right now? Take a look. If you have convolution in time, it goes to simply multiplication in frequency. But multiplication in frequency is going to be divided by 2 pi times the convolution of the function.
Obviously, I mean, it's duality.
If you work this problem, you're going to see a little bugaboo. All right, F, and I'll show you what I'm talking about. Find that for me. If you have delta, better yet, x of t convolved with h of t goes to x of omega, or capital X of omega times h of omega, right? Bring this down over here, capital X of t times h of t, right? Over here goes to 2 pi, right? Times x of minus omega, h of minus, convolved with h of minus omega. Check that out, right? Look in the book. Now, do you have it? Well, one time. Just look up, take a look at Fourier transform properties.
Oh,
Sure.
So the way the book's structured is you got convolution in one chapter and Fourier in another.
You want the properties though. Can you just do a search for, you want Fourier transform properties. Alex, you got that? I want to show you what I'm talking about because this is not right. Actually, this is right. It's x of t times h of t goes to 1 over 2 pi x of minus omega, h of minus omega. Just take a look at it. I'll show you why later. But do you all see it? Please take a look in the book. Yeah, that's it. Look at the very bottom, Marcus. Those are transform pairs, properties I need. That's transform
Oh.
pairs. I need properties. You got it? Look on the one where it says multiplication in time. H of t times x of t goes to, and it'll be convolution of the frequency, but what do you see?
It's 1 over 2 pi.
See? 1 over 2 pi. Not 2 pi, but 1 over 2 pi. I can show you why, I think, afterwards. It's not 2 pi times that. And it's going to bug you until you see it, but I can show you. All right, so what happens is, now when I take this, listen, I thought this through. I've been this route before. I've made that mistake. Now, this is the function, frequency domain. I've got to take this into the frequency domain, so this is going to be tau, right? Tau, but not tau. Now it's capital TD, correct, guys? Then it's gonna be times the sinc, now make sure you write this down, of omega TD divided by 2. Please make sure you write it down. I know some of you aren't, because it's probably video recorded, but you're gonna need this information. The book has a mistake. I want you to notice. I'm trying to tell you, you all agree with that? You agree that this pulse function right here has a width TD, right? So that means TD goes here, that's the thing it's, and it's omega TD over 2, and it's convolving that. Please appreciate what I'm saying. Are you with me?
So PTD is just like a window?
It's a pulse function of width TD. Remember, any pulse function at all, if you have P of 10 of T, the only thing it is something centered at 0 from -5 to 5
Okay, yeah, that's
of
what I
height 1.
meant. Yeah.
So it's with
So it just
TD.
cuts out everything else.
That's exactly what I want. I want a finite pulse strength.
So it's kind of like a U of T function where you limit it.
Well, yeah, you could make it out of U of T plus 5 minus U of T minus 5, but
That's how we
a
use it.
pulse is what we use. But the reason the U of T's are a pain in the butt.
They are.
This stuff is easy. All right, now here's the, so now because it's convolution, right? In the frequency domain, I gotta put 1 over 2 pi, so it kills that guy. Got me? Now I have that. Next, I need the convolution. Now here's the game here. This now looks like a constant. Doesn't look like a function of omega. This is where the omega is. Are y'all with me? What happens when you convolve a delta function with anything? It replaces the argument in anything with the argument of the delta function. That's what I want to, y'all agree with that? Are you with me on that? When you're doing a delta function, the only thing you have to do is take the omega there and replace it by omega minus n omega naught. So we're gonna do it in the step down here. I'm gonna pull out some of these constants, and somehow I forgot a tau in here. There should be a tau there too, but I think I erased it with the 2 pi. So now I have tau over t, then it's times td. Now I'm gonna have an infinite sum. I'm gonna try to write this accurately. Help me out, guys. And now we're gonna have the sinc. First I've gotta put that sinc down. The sinc of n omega naught over, or times tau over 2. And then I take this and I replace it, the sinc here, that's a sinc, and I replace omega with omega minus n omega naught, and then I put TD over 2, and lo and behold, that is the function. Now this is the Fourier transform of a P of train that has T dwell as its width. And that's the Fourier transform parameter. Please make sure you write that down.
What do you think's wrong with the book's way? Because the only difference between
This right here, sinc of x is equal to sine of pi x over pi x. That's not the definition I used. I've used the definition of x, sine of x, sinc of x is sine x over x. He uses a different definition. Just look through it. You all see it?
the form of the equation that he gets is exactly the same.
And that's the problem. He's wrong.
Oh, okay.
Because of this. Look over here. I'll show you this.
I mean, if I use your definition, then his
Yes,
formula is right.
but that's the exact problem. He says he's using one definition and he's not.
Okay.
Look at back there to where he says what sinc is.
That's hundreds of pages up.
No, it isn't. It's just up. Go up.
Is it a different chapter?
Go
Because
up.
each
No,
chapter
no,
is
it's in there. Right there, right there. All right?
Huh,
See?
fascinating.
That's where he makes a mistake. I've been down this road. I mean, the guy's not bad, but he makes mistakes because somebody put that in there after he wrote this, and they had the wrong definition of sinc. That's my point. Got it? That's right, though. And that's not quite his, because what does he do?
It uses F, but
And we have to, right now. Now we have to go back and take omega naught, and omega naught is just gonna be 2 pi F naught, right? So you're gonna get this. This becomes pi F naught. And here, get rid of that 2. So he has pi, and he has F minus F naught. And that should be what he has, I think. Take a look. Is that what he has?
yeah, I think.
Coefficient up here, he has an A, right?
Yeah.
All right. Put that there, and that's it. Now what we have to do is talk about what that looks like. It would look like this exact pulse train here, except that, the frequency domain, but instead of spikes, now we're gonna have sync functions. That's why I need that overhead right now. Let me get it up there so we can talk about it. Because we're gonna talk about something called Doppler range ambiguity, or resolution, pardon me, resolution. Is that thing still on or not? Projector shut off? No, it's still on. Can you get those lights? Anybody? Just punch it in the center and then punch, I think it's the upper corner, upper left or upper right corner, one of the two. Yeah, that's fine. Now, help me out here if I didn't get the PowerPoints in that, I wanted to go right to here. This is what he's doing, he's showing what the sync function comes from right there, and then he doesn't use his own definition for some reason. All right, that's just a sync. He shows you if you have a pulse, it goes to a sync. With me? Now, next one down there, right here, that's his infinite pulse train. But you'll notice for convolution, he has multiplications. That's supposed to be the symbol for convolution. You all see it right there, guys? That's supposed to be convolution. He's got multiplication, it looks like. Then, when you do that, if you take a look at this, he does the right thing there. That, in fact, is correct. And then he comes down here, is now he wants to take, he goes down and does this. Let me get the next page. And this is what I was showing you initially for an infinite pulse series, right? Do you all remember that, guys? Now, he goes down the finite pulse time. Now he takes this P TD of t times his initial Fourier transform, or his initial function of t. And now this is what you get. Please take a look at this carefully. What happens is those spikes are not broadened. And what happens here, this width to the first lobe, and I'll try to draw it up here, is going to be basically limited to TD. And I'll try to show you this. We could do it in the frequency, we can do it in the F domain, just for the sake of being consistent with him. All right, now, when I take a look, and I'm going to just focus in on the main lobe, the very beginning. So it has this, if you think of the magnitude right here. Please watch this. Right here is going to be something that is now, this, I should say, is 1 over TD, and this is minus 1 over TD. This is at baseband. This is the total width there, and this is in the frequency domain, and this is pulse of TD, well, sorry. I'll put the sync function down. This right here is going to be TD times the sync of omega times TD over 2, which is TD times the sinc of pi, right there, times F times TD. And this is the first thing, this is important, you see this. Right here, that 1 over TD is called the Rayleigh or Doppler resolution. It's called either Rayleigh or Doppler resolution. And it's equal to 1 over TD. Now, why does it say that? Here's why. I want you to follow me. Suppose I got something that's right here, and now I get a Doppler waveform. I get a Doppler shift, but it only shifts it out to here. Y'all see? That moves that signature a little bit. Can you discern the difference between that and that? You have to move out at least this much before you can actually get a noticeable signature change with your actual work. So 1 over TD is called a Rayleigh or Doppler resolution. And what does that mean? It means if you want very good Doppler resolution, you have to have a very long pulse string. Y'all with me on that? Now that begs the question of, well then, how long does a cop have to actually have you in that radar beam before he can collect the information? I don't know the answer to that exactly. It has to do with the size of the vehicle. But he doesn't get it instantly. Now, he does get it almost instantaneously if he has a laser. But with this, he has to have at least 1.5 seconds of dwell on your car to get a legitimate speed. All right? And that's because his range resolution needs that much collected information. Do y'all follow me on that class? Now, with aircraft, this is where it gets bizarre. The faster something's going, to know the exact speed it's going, the more pulses you have to gather in. And that means if you want the exact speed on an F-16 coming at you, you're gonna have to lay there a long time. Most times exact speed isn't the important thing. If you're within 10%, that's all you need to know. You need to know it's coming, and it's coming fast, or leaving and leaving fast. And you need that for a lot of things with armaments. But just remember that it takes a while to collect that much information, because you gotta send it, it's gotta hit the target, come back to you, right? And then you have to flip it around and do a match filter on there. And where the match filter peak is the time delay to where you are, and then the Doppler shift is observable too when they do fast Fourier transforms. We do this in chapter 14. You're gonna see some really cool stuff coming up. And you know, if I could get away with it, I will. I would love, I'm working with a kid named Luke that you know, and we're doing a paper, and we're going to actually try on radar. And it's getting rid of range ambiguity and Doppler ambiguity entirely, which is, it means you have to have an enormous amount of data stored, and you got to do it at baseband. You can never do it at high frequency, but we're going to try to build something to actually allow that to happen, and then take a look at both the spectral domain and the time domain, what's going on. And I tell you, we're gonna use things like windowing, Hamming windows and stuff like this to get rid of noise. It's gonna be a very interesting adventure, but microcontrollers are gonna be needed for that, and we're gonna probably use some, how many of you guys have programmed with microcontrollers?
I think you probably need to use an FPGA. I don't think microcontrollers can handle, unless you're just doing
FPGA just for baseband. You're thinking of high frequency sampling. We're not doing high frequency sampling. We're gonna use mixers to bring it down, but we're gonna use, once we get it down there, we're gonna use a microcontroller to do a lot of digital signal processing. Now, he's familiar with a lot of this because he's in Beverly's lab, and they do this kind of stuff routinely. But I really stumbled across a gem with that laboratory over there. And if we get this done in time, by the time you guys are doing your projects, we'll have one more presentation, and you get to see it. You all with me on what's going on here? It's Doppler resolution. And there's first the maximum Doppler shift and Doppler resolution. I got through the topics. I didn't know if I was going to make it. Now I'm going to talk a little more about what's in that chapter if I can. Does everybody understand what I'm doing so far? Now you can understand the importance of understanding Fourier theorems, Fourier transforms, but this is all in continuous time for a reason. It's easier to understand. What we're really going to do is chapter 14 in a bit. That's discrete time Fourier series analysis. The DTFT, the Z transform. By the way, the Z is akin to a Laplace. And the reason Laplace is so important is why, because you can build circuitry to do the filtering for you, right? Now you can do a lot of things that you need to do for radar signal processing, like getting at clutter. That's another issue. Let me just take you through the rest of this chapter right here. Y'all with me there? Now here's the next thing he does, and I can do it, but I don't think I need to do it. What happens when you take the thing and you bring it, not a baseband, but you beat the signal up to the high frequency component? Help me out here. If I have f of t times cosine of omega naught t, and I know f of t goes to f of omega, what happens down here? Do y'all remember? This is the cosine transform. You're going to get two pairs, right? There's a weight of 1/2 that comes in the front of it, but then it's going to be f of omega plus omega naught plus f of omega minus omega naught. I always do this in omega because you saw omega over and over again when you were in signals. You didn't use f. If we decide to use f all the time, we will, but it's a scale factor of 2 pi. Agreed? Now, what does that mean? It means whatever this signature is in the frequency domain right here, it simply is jacked up and pulled down to the actual frequency that it's transmitted at. Does everybody understand that? Everybody? Okay, that's important to understand. And there's a few other things that you have to understand too about that. I'm going to take a look. I don't want to draw this. I'm going to just go to where he has it.
My Fourier transfer table has a pi out in front.
That's because it's an F, right? It's an F, not omega, isn't
No,
it?
it's an omega.
That's for just the
Well, it's not
cosine.
an
That's
F.
just the cosine. It's not f of t times cosine. It's just cosine of omega naught t.
Well, for u of t, it has the same thing.
Look at your properties, Fourier transform. Is that Fourier transform properties or pairs?
Pairs.
Look at Fourier transform properties
Okay.
and look of f of t times cosine omega naught t.
Well, that's not on here, so.
Look at sine omega naught t, or e to the j omega naught t. There has to be one of them. Yeah. Well, it's right here. F of t, it's f minus omega naught. See that? All right. Anyway, a cosine, the reason this, see, a cosine is what? It's e to the j omega naught t minus e to the j omega naught t. E to the j omega naught t plus e to the minus j omega naught t over 2. The 2 comes over scales, these 2 are just shifted. That's it. Now, next, bear with me on this, guys. I'm trying to do this so you can see. Are you on this page right now that I'm on?
I can do.
Well, I'm just.
Yeah, I am.
All right, I don't know what you're doing half the time. Now he's going to go ahead and he's going to do the transform, and he's going to show you that in fact when we send a real radar signal, if you look at this, this is a real radar signal when it's modulated. He's assuming that this is the high frequency carrier. Frankly, Luke and I were doing some stuff with it. There's about 10,000 to 100,000 cycles in a typical pulse on the on-time tau. So you have to have about over 100 for something called the beam, or for the actual impedance of the antenna you transmit on, to look at it as if it's a continuous time wave. If you don't have a whole lot of cycles feeding that antenna, you just get a transient response from the antenna. So you have to have a lot of cycles in order for it to act like an antenna at that frequency at F0. Follow me? It can't be one cycle. It just will not act. It'll look like a transient. So what does this look like in the frequency domain? That's the reason I'm using his. Well, it'll be centered at plus and minus F0 if you're in the frequency domain. Then you would have that exact envelope we had back at baseband moved up there. Now you can see if that's in the frequency domain there, continuous time. Once we start sampling and doing discrete time processing, all that is dulled. I'll use that. The sharpness, the crispness gets dulled. And that's where all the really clever signal processing comes in. Stan Reeves and some of the people that do MRI image processing know a lot of tricks to how to pull signal out of noise, and it's through coherent processing and filtering. Have you ever seen things where they take, we'll get to the digital stuff in a second, where they take like a picture and they blur the heck out of it, distort it, and then they use something, this is a signal processing method, and they recapture that information, the original information. That's signal processing, getting rid of distortion. There's distortion that Doppler shift undergoes. There's distortion that ranging gets, and there's all sorts of ways to mitigate that, and that's some of the fun stuff coming up. But you have to be aware that, when you get a radar picture, just understand you're not looking at time domain. The thing that's rendered to you is something in 2D usually, where targets are. Sometimes 3D. Not just where the target is, but its velocity. That's what you want clear, so you can see it with your eye and make a decision. You don't want a bunch of data, like numbers and stuff. It makes no sense. You want something that's rendered in a way you can interpret it and make a decision. And that's where all this image processing comes in. It's usually 2D fast Fourier transforms they use for a lot of this. There's other stuff. It's really clever too, by the way. They use, a lot of times when they capture the data originally, they're using, after they get to baseband, they use finite impulse response filters. They actually do the filtering in the time domain with a truncated h of t, not h of omega. And I think you know what I'm talking about.
Yeah, it's kind of JPEG compression. I wrote a JPEG compressor, and it uses discrete cosine transforms, looks at the power spectrum, and it reduces it.
All right, now I'm going to try to show you this. I got to amplify this or blow it up a little. If you have it open, I know there's a couple of laptops here. Bring your laptop. What I want to show you is what happens when you get a target moving. When you're sending and receiving a signal, now he's not using a match filter, this is raw data. This is what you'd see if you just did the Fourier transform, and it's in continuous time. It's not what you're really going to see, but it's giving you a picture of what goes on. Now, you see, if you have, this is going to be the clutter that's not moving. He's assuming the radar stationary. You see this peak right here I'm pointing at? That target right there, you see a target appear where there should be a null. That's a target. Now here's the crazy stuff. He didn't use a match filter on this, he's showing you the raw data. Now really this stuff's jumping around, there's noise on. If that target's not above the threshold, and they go through all this probability stuff, you don't see it. It's a mess. Once we do the match filtering, that target will stand out when we do something called the ambiguity function. It becomes something that is there and it's obvious, but that requires some filtering. Here's the Rayleigh main lobe resolution I'm talking about. It's usually called the Doppler ratio. It's 1 over TD. And it's in Hertz, not in omega. So then, let me go to the next page. Let me unblow that thing up. What he's doing is showing you several different things that can happen here. And I'm going to tell you one thing, that I don't have time today to get into this, but we're going to get into this. This is continuous time. But you can just think, if you have two different moving targets, both the size of the moving target, right, and the amount of clutter in the background determines your actual signature you're going to see, right? So the more clutter, the more of this original signature unshifted coming back at you, the less you're going to actually be able to see in terms of the target. So that's why we do clutter filtering and things like that. It's coming up, and that's in the ambiguity function. But he's giving you a picture of what happens. What are some of the problems with resolution if you don't have enough? And you can read that on your own. Now, somebody mentioned this. Marcus, it might have been you, about receiver bandwidth, limiting a lot of stuff. Receiver bandwidth is something that's very important for the actual tau. It's the small tau, because 1 over that, the bandwidth has to be at least that. And when I say bandwidth, I got to tell you one other thing too. Amplifiers, in this book, he's assuming amplifiers have a flat amplification ability. In other words, the frequency at F0, if you put in a certain power P1 at frequency F0, the amplification on that would be the same as if it was 2 F0, and you would see that. Well, over a band of frequencies, over a bandwidth, and at baseband, really this is done probably at the intermediate frequency, but if you look, this is what we'd like at baseband. If this is F bandwidth here, F minus F band, we'd like it to be flat with just A, and this is versus F, right? But here's what you really get on amplifiers. All right, so what they have to do with most amplifiers is spend some more money, and they're going to take this signature and they're going to take 1 over that signature. They're going to find something when I multiply this signature by that, I retain that. Now that's money. Sometimes they don't want to do that. Do y'all follow me on that? This is the thing what Bose did with his speakers. Professor Bose at MIT got fed up with lousy speakers, so he took lousy ones, got their frequency characteristics, the power versus frequency response, and he just built the filter so that now, no matter when he puts in 1 watt at any frequency, he gets 1 watt out of those speakers. And that was the Bose 901 back in about 1979 or so, 1978. And then I don't even know what they have anymore, but that was an active crossover. Well, it's the same thing with amplifiers used for high frequency signal processing. They need the bandwidth and they need flat amplification. And that becomes a problem. Now, I've never built a receiver at very high frequencies. We built some stuff, but it was a baseband basically. All right? Some of the stuff that they're doing at intermediate frequencies, what's intermediate now? 365 kilohertz? I mean, what's your IMs for your radio when you have your radio lab?
200.
200 what, kilohertz?
Yeah. Well, so, but typically, like a real radio would do 370
370 kilohertz?
for AM, yeah.
That frequency is not that overwhelming. That's doable for even a relatively cheap op amp and stuff like this, but when you're talking about 30 megahertz and higher kind of stuff, it becomes a problem to get any bandwidth that's substantial. By the way, you don't understand exactly what I'm saying, but when they talk about bandwidth, a lot of times they talk about percentage of the carrier. So when you're at 9 gigahertz, 10 gigahertz, if you have a 10% bandwidth, that would be 1 gigahertz. That's enormous. It's an enormous amount. And if they want digital sampling and stuff, that would take an enormous bandwidth. That's the reason they bring it down to baseband. Normally at that frequency, you're only going plus or minus probably a couple hundred megahertz at most. You're not doing, and that's at most, you're not doing wideband. Now there are wideband radars that I'm studying, and I'm seeing nothing but nightmares, but they do work. You know, the reason they use wideband is basically it gets through everything. You can't mess with it. It'll get through everything and give you some information back. But to my understanding, the signal processing is a nightmare. Am I over?
Yeah.
That's not right then.
That one's 5 minutes slow, so.
All right. Guys, I hope you understood this lecture. I'm getting at this part. I'm going to give you problems. Now for Thursday, I've been thinking about this. Do you feel equipped enough to take a quiz with your book open on some of this stuff? In other words, I will let you use the book because it has some of the information. If you want to bring a supplemental Fourier transform table, go ahead. What I don't want you to be doing is scratching in your head saying, I don't remember the sine is multiplying this, and what happens, Dr. Pickens? You see what I'm saying? You're rusty on that. Yeah.
Can we just bring the linear signals book?
Yeah, bring it and bring this book too. But, all right, no open laptops, all right? Who doesn't have the book?
So I would argue that a quiz is not nearly enough time to reference a book.
I'm just talking about the transform tables in the front. I'm not going to do, you need to know your transform pairs is what I'm getting at.
Right.
All right, and I don't feel like providing it, so bring your own. You're